Hello, so this is a revision video for APChemistry 2.1, Types of Chemical Bond. It is a revision video, so there aren't really many explanations. For full videos and lessons, please check the links in the description below. This is just what you need to know for revising for 2.1. Ionic bonding is the electrostatic attraction between oppositely charged ions. It usually occurs between metals, which form positively charged ions, and nonmetals, which usually form negatively charged ions. Be careful, however, because it doesn't have to be between metals and nonmetals. For example, ammonium ions are positively charged and also form ionic bonding with negatively charged ions. Covalent bonding is the electrostatic attraction between the nuclei of two atoms and a shared pair of electrons. When two electrons get shared between two atoms, the positively charged nucleus of each gets attracted to the shared electrons, and this pulls the two atoms closer together. Sometimes two atoms will share more than one pair of electrons, forming double and triple bonds. Single bonds contain one shared pair of electrons, double bonds contain two shared pairs of electrons, and triple bonds contain three pairs of shared electrons. The more electron pairs there are shared between the atoms, the stronger the bond. Covalent bonds can be either nonpolar or polar. Nonpolar covalent bonds form when two atoms with the same or similar electronegativities bond together. This means electrons in the bond are equally shared between them, and neither atom ends up with a partial charge. Polar covalent bonds form when there is a difference in the electronegativity between the two bonded atoms. The bonding electrons are pulled closer to the more electronegative atom, giving it a partial negative charge, and the atom with the lower electronegativity has a partial positive charge. For example, in hydrogen chloride, because chlorine has a higher electronegativity than hydrogen, the bonding electrons are more attracted towards the chlorine atom, giving it a partial negative charge, and that leaves the hydrogen atom with a partial positive charge, and the covalent bond becomes polar. It's important to remember that ionic and covalent bonding are the extremes of a continuum of bonding. In reality, most bonds exist between the two extremes. The greater the difference in electronegativity, the more ionic character the bond has, and the smaller the difference in electronegativity, the more covalent character the bond has. Exam tip here, remember it is the difference in electronegativity that determines the bond type of two bonded atoms. It isn't the individual electronegativities of the atoms. You can have two highly electronegative elements bonded together, but if the difference in electronegativity between them is very similar, the bond will still have a very low polarity. For example, using Pauling values, we can see that sodium chloride has a very high electronegativity difference between the atoms involved, meaning they exist as ions, and that means we have ionic bonding. Hydrogen chloride has a slightly smaller difference in electronegativity, meaning we have a polar covalent bond, and in Cl2, chlorine, because the two bonded atoms are identical, both chlorine, they have the same electronegativities, and therefore the bond is nonpolar covalent. Ionic and covalent bonds also give different properties to compounds. Ionic compounds typically have high melting points, meaning they're a solid at room temperature. They can conduct electricity when dissolved in water or molten, because charged ions are free to move and carry charge, and they form crystalline solids. Covalent compounds, however, typically have lower melting points and are often liquids and gases at room temperature. They don't conduct electricity because there are no charged ions that are free to move, and they usually exist as molecules rather than charged ions. Finally, we have metallic bonding. In metallic solids, valence electrons are delocalized, meaning they aren't bound to any one atom. This means we can imagine we have positively charged metal ions surrounded by a sea of delocalized electrons. There is strong attraction between the positively charged ions and the delocalized electrons, and this pulls them all closer together. Because the valence electrons are delocalized, the electrons are able to move freely through the structure. This helps explain some key properties of metals, such as their electrical and thermal conductivity, and their malleability and ductility.